Okay, a factorization of a matrix is an equation that expresses A as a product of two or more matrices. So what we're going to be doing is looking at ways to factor a matrix. Now the reason to do that is that sometimes it helps break it down so that it's more manageable when you're doing calculations with it. So this first type is called the LU factorization. So the times that this is very helpful is if you end up having a bunch of equations such as ax equal b1, ax equal b2, and so on, so that they're all using that same coefficient matrix. Now, you could solve for A inverse first, and then you'd be able to have that x is equal to A inverse times b1, and x equal to A inverse b2, and so on when you're solving that series of equations. But it's usually more efficient to actually solve the first equation by doing some row reduction, getting this LU factorization at the same time, and then using that to solve the remaining equations. So it's all about efficiency when you're working with computing abilities. Okay, so assume that A is an M by M matrix that can be row reduced to echelon form. So, and first we're going to look at situations where you can reduce it without doing the row interchanges. That complicates this process a little bit, but so you have to keep up with any of the row interchanges that you do. But for now, we're just going to assume that we're not going to require any row interchanges. So then A can be written as L times U, where L is an M by N lower triangular matrix. That means that the only non-zero terms are down in this lower triangle below the main diagonal, and up in the upper triangle it's all zero. So lower triangular means the non-zero entries are in the bottom triangle below the main diagonal. U will be an M by N matrix that's in echelon form for A. Okay, so L will be a square matrix, M by M. U will be an M by N, where A was an M by N matrix to begin with. Okay, so this factorization is called an LU factorization. The matrix L will be invertible, and we call it a unit lower triangular matrix if we have all ones down that main diagonal. Okay, so now when we're solving equations, systems of equations with a matrix A, if we can rewrite it as this factorization L times U, then this equation that we're trying to work with, then the A can become LU. So we've got AX equal B. We're replacing the A with LU. Okay, and then we're going to look at this, rearrange it a little bit, and we're going to solve L times UX equal to B by doing a series of two things. We're going to first find this UX. We're going to let the Y be equal to UX. And then once we get that, we're going to replace the UX here with the Y. And so the first system we actually solve is LY equal to B. So we're just replacing the UX here with the vector Y. So solve this first, because we've got the B here, we're going to have the L matrix, and we're going to find the vector Y that satisfies that equation just by a simple solving a system of equations. This is really easy because the L is lower triangular, and I'll demonstrate that in a minute. But because you've got the lower triangular matrix, LY equal B is very easy to do even by hand. Okay, once you calculate the Y, then we're going to go back into the original equation up here and find what is the X that makes UX equal to the Y. And so then we'll be able to calculate our X. Okay, so those will be the steps. Find the LU factorization, then let Y be the UX, solve LY equal to B for Y, and then come back and figure out what the X is, just using the matrix U. And again, U is an upper triangular matrix, so that the only non-zero entries are up here, and so all those zeros are going to make that one an easy one to solve as well. Okay, so I want to verify first that this really is equal to A. So here is a lower triangular matrix, and here is an upper triangular matrix. Notice the zeros in the upper right-hand corner for L and lower left-hand corner for U. Okay, so I want to show that this product is equal to the A. So first row, first column is the 3. first row, notice the first row times any of those is just giving me that first row of the matrix. Now the second row of L times first row of U will just be -3. Second row of L times the second row of U will be 7 minus 2 is the 5. Second row times the third column of U will be 2 minus 1. So here's our 1. And then the second row of L times the fourth row of U will be -2 plus 2 is 0. Okay, now we're on the third row. Times the first column will be just 6. Third row, second column will be -14 plus 10, or -4. Second row, third column will be -4 plus 5 minus 1. And then third row times the fourth column will be 4 minus 10 plus 1 is -5. Okay, and now the fourth row with each of the columns. With the first column is -9. The second column will be 21 minus 16 is our 5. And then we'll have 6. This column, fourth row, third column will be 6 minus 8 minus 3 is -5. And then finally the last column with the last row will be -6 plus 16 plus 3 minus 1 is our 12. So it does multiply to be the A, and we do have the proper forms for those two matrices, the L and the U. Okay, so now we're going to use the LU factorization to solve where this is our B. So again, we're going to solve AX equal to B that by replacing the A with LU and then regrouping this as U times L times UX equal to B. So step 1 is we're going to let y equal u times x. And so this equation becomes Ly equal to b. And so we're going to solve that. So solve Ly equal to b for y. Okay, so I'm going to write the L down. Now we could do this by row reduction, making the augmented matrix, taking L with an extra column for the B. But I want you to see how easy this is. I mean, it'll be easy with row reduction because you've got all those zeros already up on top, above the pivots. But I want to show you how easy it is. Okay, now notice here, if I go back to actually writing this as equations, I would take row 1 times the vector, and I would have y1 equal to -9. And then the second equation is that -y1 plus y2 equal to 5. Okay, 2 times y1 minus 5 times y2 plus y3 equal to 0. And then -3 y1 plus 8y2 plus 3y3 plus y4 has to be 11. Oops, 7. Okay, so we already know y1. And if we plug in -9 for y1, we'll have 9 plus y2 is 5. So that means y2 has to be -4. Now we know y1 and y2, so this becomes -18 plus 20 plus y3 equal to 7. So that means that y3 is equal to 5. And now substitute those in. Okay, and this is called back substitution. So now I'm going to substitute those values in. So I've got 27 minus 32 plus 15 plus y4 equal to 11. That means y4 is equal to 1. So it's very quick to get y once we had that L as a triangular matrix. Okay, so now let's solve ux equal to y. And our y here is the vector -9, -4, 5, and 1. Okay, so writing the u down, We have 3, negative 7, negative 2, 2, 0, negative 2, negative 1, 2, 0, negative 1, 1. This is times our x, which will be x1, x2, x3, x4 equal to the y. And again, we could do this by row reduction, set up an augmented matrix and do row reduction, but I'm going to do it by hand just to demonstrate how easy it is. It's not very many calculations and it's very quick. Okay, so rewriting the left side as a system of equations, we have minus 1 x4 equal to 1. I'm just taking the last row here times the vector x and equal to this entry. And now the third row will be minus x3 plus x4 is equal to 5. And now the second row, minus 2x2 minus x3 plus 2x4 has to be equal to negative 4. And then finally, the top row, 3x1 minus 7x2 minus 2x3 plus 2x4 is equal to negative 9. So now, we know from this top one that x4 is negative 1. Plug that into the second equation, and we get minus x3 minus 1 is 5, which means the x3 is going to equal to negative 6. And then plugging those two values in, we have negative 2x2 minus the x3, so that'll be plus 6, plus 2x4, so that'll be minus 2 equal negative 4. So that means x2 is positive 4. And then finally, in the last equation, we're looking for x1 now. 3x1 minus 7 times x2, so that's minus 28, using this x2. Minus 2 times x3, so that's going to be plus 12, using this. And then minus 2, plugging in the x4, is negative 9. So that means that 3x1 is equal to 9. So x1 would be equal to 3. Okay, so we used the LU factorization to solve this for x. Our x came out to be, the x1 is 3, the x2 is 4, the x3 is negative 6, and the x4 is negative 1.